Hi, everyone. Thanks for the invitation to a fantastic workshop, which has been going on for a couple of years, and it's such an appropriate venue for mathematics and for exploration of mathematics and machine learning. So I want to talk to you about. Also, first of all, I should apologize if some of you have been in a recent talk about this. So I hope you brought a pillow. Today, I'm going to talk about conjecture generation using machine intelligence. So conjectures are an important building block towards the discovery of mathematics. Historically, there have been numerous conjectures which have not only been insightful in a particular problem at hand, in a particular domain of mathematics, but they have also been important in driving the development of mathematics itself. Conjectures by André Weil and Hilbert's list of 23 problems, for instance, are good examples of interesting conjectures that have shaped development in pure mathematics for decades. So, of course, machines seem to be better at spotting patterns in mathematical or other kinds of data than humans. So we thought it might be a worthy enterprise to understand if we can use or exploit machine intelligence to conduct a search in a space of conjectures and produce some non-trivial statements that may or may not be true. So sorry, there's a message. I hope it's oh, it's just a good morning, everyone. So in the year 1900, Hilbert presented a set of 23 problems at the International Congress of Mathematics in Paris. Now, it's not well known, but one of those problems was solved the very same year. Not all of these problems that Hilbert suggested lasted for eternity. I wanted to talk to you about the 13th problem to which Hilbert returns in the 20s when he writes about these problems, and he devotes 5 of 8 pages talking about this problem. But this problem is quite interesting to me because it sort of highlights how an important mathematical conjecture can not only drive development in pure mathematics, but also in other associated fields. So 13th problem is actually pretty easy to state. So Hilbert, for some reason, asked the following question. He asked that given a degree 7 equation and the fact that it can be reduced to a form that you see on the slide, can one write down the solution as a composition of a finite number of 2 variable functions? Of course, as we can see, there are 3 parameters in this equation, so the solution must be a function of 3 parameters. But does that form lend itself to a compositional structure in terms of functions of 2 variables only? Now, fast forward 50 years, Soviet mathematicians Kolmogorov and Arnold had to look at this problem. In fact, they had a supervisor-supervisee relationship, and they got into a friendly mathematical wager about one version of this problem. So although Hilbert originally posed this question for algebraic functions, Kolmogorov and Arnold ended up resolving the conjecture for continuous functions. And the result was a mathematical supernova. In fact, Arnold, who was only 19 years old at that time, putting a lot of us to shame, showed that only 2 variable functions are required as they made progress. The resolution to Hilbert's 13th problem, a la continuous functions, yielded the Kolmogorov-Arnold representation. So the Kolmogorov-Arnold representation looks handful on the slide, but what it truly says is, if you think of f as a multivariate real function, then you can always write down the function exactly as a combination of certain functions, but the number of arguments in these functions is just 1. So it's not 2 as originally Hilbert had suggested. So what this really means is something quite profound. It means that the only non-trivial function in the real domain is the sum function. This is a bit mind-blowing. And not just that, the functions that appear on the right-hand side of this representation, they end up having a neat geometric interpretation as well. So, fast forward 3 more decades, and in the 80s, machine learner Robert Heck Nielsen came across this representation and immediately realized that, wait a minute, this compositional structure looks exactly like a 2-layer neural network, which he then goes on to build, and he names them Kolmogorov mapping networks. But lots of us who also use machine learning in our work, where we sort of are aware of these universal approximation theorems that came about in the late 80s by Cybenko and Hornig. They sort of showed that neural architectures are capable of approximating reasonably well-behaved functions to an arbitrary degree of accuracy. However, the network that Robert Heck Nielsen built, they are 2-layer networks, and they are not an approximation, they are exact. So this begs the question that are these 2-layer neural networks practical? But before that, it actually gives you an idea why neural computing has meaningful mathematical foundations. This representation effectively shows that a 2-layer neural network is capable of representing any real continuous function, although the network itself, the details of the architecture, such as activations and all, are wildly behaved functions. And not a lot of people are working on employing these networks to real tasks, but it establishes why deep learning actually works. So if you can approximate if you can write down this representation for any real continuous function as this compositional structure, but the functions that appear in this structure are wildly behaved, the reason deep learning works is as you add more and more layers, you're effectively controlling the wild nature of some of these functions on the right-hand side. And then you get into the domain of approximations, and all is well. One can hopefully recover the universal approximation theorems. So this problem was quite interesting. Over a period of almost a century or so, it ended up having grand impact in functional analysis as well as geometry, and also showed why neurocomputing is on the right track. But this conjecture is quite interesting, but it does beg the question, how do we come up with good conjectures, or what constitutes a good conjecture? So just a couple of years ago, Robert Dijkgraaf wrote a very interesting article in Quanta, and I encourage everyone to read it. And he called it the subtle art of making conjectures. And what's a good conjecture? The fact that n is less than 2 to the n is a conjecture. It's true, but is it really worth our time? Is it interesting enough? So it turns out that it's a meaningful question to ask. What makes a good conjecture, and list out certain criteria that potentially make sense. So Robert Dijkgraaf noted that, okay, first of all, a good conjecture must be non-trivial, which we can all agree with. Potentially, a lot of evidence supports that conjecture. And this is true for many conjectures in mathematics. Just for an example, Goldbach's conjecture is one. If one puts on the theoretical physicist hat, then one might be able to argue that a good conjecture in the right representation must be terse. It must look nice. Then there are conjectures that have a special status, such as the Riemann hypothesis, where it's not even called a conjecture anymore. It's a hypothesis, although it's unproven. The power of Riemann hypothesis or conjectures of that stature is that they can unlock new avenues for mathematics. They can unlock new theorems. They can unlock their own universes. Presumably, Robert Dijkgraaf reached out to, remembered some comment from John Conway, who said that a good conjecture must be outrageous. And outrageous conjectures are potentially more interesting than n less than 2 to the n. So Raw diagraph also says that if a conjecture is proved within a few months, then perhaps its creator should have pondered it a bit longer before announcing it to the world. Of course, we're often shy in announcing, such things, but we will patently ignore this advice for the moment. So let's begin by talking about what our strategy is, or what class of conjectures might one be interested in looking at. So the class of conjectures we are sort of interested in are inequalities. So things of the type f less than g, where f and g are continuous functions for the moment. This is our setup. Now, post facto, we ended up discovering that there's a fantastic book on inequalities by Hardy, Littlewood, and Polya, slightly less than 100 years ago. And they sort of opined that it would be a useful resource for mathematicians to have a lot of conjectures or theorems on inequalities listed out. But there was no unifying theme per se. So this is why things became interesting, because they also have got a huge repository of conjectures, and it seemed like a worthwhile enterprise to have a look at this class of conjectures. Now, broadly speaking, our strategy is quite simple. We wish to understand if there is any structure to a well-defined space of conjectures of this type, and can we exploit that structure and interact with domain experts in different mathematical domains to come up with interesting, non-trivial, or even outrageous conjectures, and sometimes we might even be able to prove them. So this is an oracle that we aim to build. So before we define the space, I thought I'd introduce symmetry as an organizing principle that theoretical physicists and mathematicians have benefited from for centuries, well, at least a century. So in this context, we are sort of quite interested in formulating a space of conjectures whose symmetries we understand, and when we try to solve a very high-dimensional optimization problem, perhaps symmetries are going to come in handy. So let's consider a space of relations and a space of conjectures. So we think of a tuple of functions f comma g such that they are well defined on some compact set D. Now, the talk is not very technical, so I'm giving you broader details, but a space of relations. So the space R consists of all pairs of functions such that f and g are in some space of continuous functions defined over some domain, which are called D in the slides. Now, in this space, there is no presumed relationship between f and g, but embedded within this space is a space where f and g are related by this strict inequality. So the conjecture space is embedded in the space of relations. So one interesting point is, what about the point 0, 0? So 0 is clearly not less than 0. Thank you. So it can belong in the space of relations, but it does not belong in the space of conjectures. Now, given that we have defined such a space, we are introducing the notion of a space of conjectures. We wish to ask some group theoretical questions. But But even prior to that, it's interesting to consider the act of defining such a space in the first place. Should such a space exist that exhibits some structure is a question that we looked at, and we asked ourselves the following question. We asked, what is the largest group linearly acting on this space of conjectures? Now we are beginning to understand the structure of this space, and we can only go so far without placing any conditions or restrictions on the function classes themselves. So we will keep things as general as we possibly can so far. So we asked the question, given this space, what is the largest symmetry group acting linearly on C? Now, when I have discussed this work with some mathematicians, often I have been met with some surprise. So some folks have pointed out that why do you expect a group structure here in the first place? And when we show that there exists a group and we prove that it is a group, one can realize by attempting to prove it's a group that it is non-trivial. So perhaps it is indeed slightly surprising that there is a group structure here. The second question we wanted to ask was, are there any free group actions on this space? Now, why would we want a free group action? For obvious reasons. If we have a free group action, then we can take a quotient of the space and conduct our our investigations on such smaller spaces. So in fact, those of you who are very familiar with machine learning or symmetries, forgive me, but we are effectively saying that this is a space of conjectures, C, and upon quotienting by some freely acting group, we might be able to move under the orbits of this group. And that might create some nice partition of the space itself. So computationally, when we are looking at this space, we don't have to explore the full space. If it already has structure, we will get away with some canonical equivalence class and just studying it. The second reason for wanting a free group structure is when we do specify certain function classes, then perhaps the manifold C itself can be realized as the invariant ring of the free group action. So this sort of goes along the lines of the typical strategy in classical invariant theory, where you ask the following question, that given a group, what is its invariant ring? And the second important question that also appears in some of Hilbert's original problems, the second question is the ring of invariance finitely generated? Now, this is an important question, because then what it means is, if we are talking about the conjecture space and we have got an invariant theoretic description of it, then and the ring of invariance is finitely generated, then it is much easier to parameterize and conduct search over this space. So this is why we are interested in understanding group actions on this space and computing invariance down the line. Now, we totally expect things to be complicated, since we have not specified function classes per se. And there will be situations where you might need some more involved tools such as geometric invariant theory to cut out bad orbits from the points that are fixed. Nonetheless, there are many group theoretical questions that we pose to ourselves, and we were able to answer a couple of them. Right. So the group that we sort of wrote about in our work on this is denoted by this curly G. And it sort of got a unique decomposition in terms of this matrix. So A is an element of this group, capital A, and you can see that there are 3 parameters on this. And those of you who are very familiar with quantum computing, for instance, will immediately recognize the constant matrices on this. Any guesses? They are Hadamard matrices, and there's a unique representation of our group in terms of these matrices. Now, we also noted that this group is probably the simplest group you can think of working on this space. The true group action, or the largest such group action, will be contingent on us making group elements functions of where you are on the manifold. But for the moment, we don't have a good enough understanding of the conjecture space itself to embark on that. However, we'll keep talking about this group G. And we note that this group has a semi-direct product structure, which is often associated with unipotent groups. But this structure sort of captures two distinct components of the, two components of the group. One is the group of positive dilations or dilations. So no one would be surprised if one wrote down the statement, F is less than G, implies some positive constant multiplied on both sides. So that set of transformations forms a group, and that's the dilation group. So and we also show that that group is acts freely. Nonetheless, we'll come to that later. So we have this interesting product structure in the group. The remaining group is not intuitively obvious how to state that, but they sort of what they do is they do linearish transformations on the pair F comma G and preserves something. It does not preserve the inequality. It preserves this property. And the strictness of the inequality is quite important here. So nonetheless, we had posed the question: is this group algebraic? Now, the group that you see written down it can be generalized, and we have generalized that to non-positive dilation. So there are glimpses of projective geometry here, and quotienting can potentially lead to a nice description of an algebraic group here. So we sort of have realized this group as a 3-parameter group, and we show that it's a Lie group, and we show that the conjecture space is as well as the space of relations are Banach manifolds, and so all the subgroups of this group can be written down by specifying the coefficients, the parameters that we had used in the definition. So we sort of have this picture where A, B, C are the 3 parameters that define the group, and the only constraint here is B is greater than 0 and A is not 0. And we sort of list out different subgroups of this group as different planes, and we find some interesting ones. We find that there are two subgroups J1 and J2 which are maximal in some sense. Maximal meaning there isn't a subgroup of G that contains them and is also freely acting, and that is provably so. And we also show that these various groups are also matrix Lie groups, and the whole endeavor around understanding symmetries or automorphisms of this space sort of opened up a lot of questions, and we hope that as this framework is developed over time, we might be able to feed some of these insights into our oracle. So if you're falling asleep by all the random group appearance of group theory, then let me wake you up by showing you how the process of conjecture formation works in this framework. So we have some latent space that guides you on the space of functions. So that latent space is sort of hidden away here, and there's a mapping that where one can invoke lots of machine architectures, or even put simple ansatz. So the latent space sort of captures information about the space of relations, and following that, we sort of say that, okay, this is actually now a sampling problem, because when you start at the beginning of this red line in somewhere in the space of relations, and you can guide yourself by simple algorithms like gradient descent, and as soon as you hit the conjecture space, lo and behold, you've got a conjecture. Now, so that seemed like an obvious strategy to us, and a lot of interesting insights have been pouring through the theory we are developing simultaneously. But even the most basic version of this algorithm seems to give you conjectures, and we're quite surprised. So I remember the first time I coded this up, I was flabbergasted, because one of the conjectures we ended up finding was number 5 on this one. So and I'll tell you about it in just a moment. I forgot to introduce what classes of conjectures we are considering here at the moment. So of course, number theory being completely out of the range of my expertise, I thought that must be the first thing I should try. So we ended up reproducing quite a few well-known conjectures in number theory, but we also generated loads of them. Now, as I show you this table, I'm remembering Robert Digraph's advice that I should have waited before announcing it to the world. But here we are, and here the conjecture is about the prime counting function. And the prime counting function counts number of primes less than or equal to x. So we wrote down quite a few conjectures, and we also combine arguments in symmetric ways using invariants of the symmetric group, and we write down conjectures that we thought were interesting. Number 24 was interesting on the face of it, but perhaps it doesn't go beyond the coincidence that it looks like describing the exterior points of a simple elliptic curve, where the y coordinate is sort of treated as the prime counting function. So yes, so number 5 on our list turned out to be the second Hardy-Littlewood conjecture from exactly 100 years ago. So was quite surprised by the fact. Well, was quite surprised when he churned this out, because it looked very simple, and I was remembering Robert Digraph's advice. So it looks simple, and then upon simple Googling, it was revealed that this is indeed the second Hardy-Littlewood conjecture, and turns out it is still unproved. And there is expectation in the mathematical community. I don't know if there are number theorists around who can correct me, but there is expectation that this is potentially false. But the counterexample to this conjecture lies for very large values of A and B. So it's a bit difficult to resolve. We had time to look at one of the conjectures that we produced, which is number 1 on the list, and this we were able to prove. So when we came up with this conjecture and we were struggling to prove it, one did what one does in this venture. So we emailed Yang this conjecture and said, Yang, we cannot prove this. So can you help? So this is Yang's proof that we have clearly butchered. That's a proof of our conjecture, and is therefore a very trivial theorem involving prime counting functions. But nonetheless, this wouldn't have been obvious to us were we staring at a bunch of data, and usually, well, trivial statements about the prime counting function, such as anyone can construct, can easily be one can easily do a sanity check on this by looking at behavior for large X. But here, Yang pointed out that we should use process inequality, and that should do the job. And indeed, it did. And in fact, although we sort of show that this theorem is true for all x, y greater than or equal to 17, I suspect this is also true everywhere. That's the conjecture from this conjecture. Okay.
Here, what's the proof of symmetry?
Sorry?
Your general presentation, it was a symmetry, proof of symmetry.
Yes.
In this example, what's the proof?
So the role of symmetry will only start becoming very useful when the curse of dimensionality hits us. So the whole idea is that when we are using machine learning to come up with statements like this, we want to reduce our search space. So we are not doing that effectively. I'm telling you results from very basic toy versions of this algorithm. We need to compute invariants and such down the line to actually take advantage of this. But right now, the idea would be that instead of conducting, search over this, whole space, you're sort of conducting search over a smaller region.
Here is no.
No. Yeah, here the manner of arrival to this statement relied on our oracle that I was writing down here. And here, actually, there is there's a couple of inputs from theory that will guide the oracle. So one being symmetrical in space, but also one can do geometric gradient descent on the space. So we'll need to define we'll need to have well-defined metrics on our space, which will also be metrics on the space, which will allow gradient descent in a geometric fashion. The loss function will also become a member of the invariant ring. So as soon as you hit one minima, you're immediately connected to several others through the group action. And if each minima, if we can be clever enough to find to ensure each minima is an important conjecture or a valuable conjecture, then that immediately gives us access to various other conjectures. But there are loads of group theoretical questions to be resolved here. We need to first generalize our group to a situation where it's also a function of your variables. Did I answer the question?
Yeah.
Okay. Right. So we also tried it at Oracle at various other things, one of the things we tried it for was finite simple groups. Finite simple groups are quite interesting there's some previous work that I was doing with Yang and Vishnu and one of our students, Max. And we're sort of trying to follow up on some of Yang's work on machine learning finite simple groups with Min-Hyung Kim, and that sort of yielded a new theorem where we had a completely different approach. So we sort of have a traditional machine learning approach where we try to learn a property using a clever architecture, and then we try to extract details from that architecture to distill out a theorem. And that theorem, we haven't written it up yet, but that theorem places necessary conditions on generators of finite non-abelian and simple groups. So we thought that perhaps even in this work, it might be interesting to try and generate conjectures about finite simple groups. Now, I'm sure everyone is familiar with simple groups, but if not, simple groups are like the primes of groups, and you can decompose your favorite group as in terms of these simple groups. And through the course of the work I was doing with Yang and others, I come across this interesting conjecture by Laszlo Babai from the 90s, and he sort of made the statement which you see at the bottom of the slide. He said that imagine H is some non-abelian finite simple group, and you are able to generate a graph associated with it called the Cayley graph, and you are asked the question, what is the diameter of this group? And so Babai effectively, he conjectured that the diameter is upper bounded by some nice function of the order of the group. And no one in the maths community knows what C is, but people suspect it is 2. Nonetheless, we sort of worked with the situation where we were studying subgroups of Sn that are finite and simple. And using that data set and our oracle, we ended up generating a bunch of conjectures. Now, presumably all of these are false, but I don't know how to resolve them. But I also deliberately wanted to show a couple of ugly looking examples, number 3 and 4. There's always a danger that when not working with finite fields or with real numbers, there are computational things to address here, such that we don't get ugly looking conjectures such as this. Nonetheless, here, conjecture number 1 says that the diameter of the Cayley graph of a finite non-abelian simple group is lower bounded by the average of the traces of your generators, for example. We also have bounds in terms of the orders of the group generators as well. And all of this works because finite simple groups are 2 generated, so we're good. Yes. So there are some other applications we have tried but not reported on. If you're interested, you're welcome to come chat with us or on your favorite application as well. So we will look at some classes of random matrices such as Wigner matrices. And what we can do using this formalism is also generate probabilistic conjectures. So we can make statements that might be true or that are conjectured to be true on a huge volume of data. And we have such statements, although we don't have a specific question we're looking at in that sector. Right. Now, there's often a niggle that, okay, many interesting relationships in mathematics are also in terms of inequalities. And we sort of realize that the case for equalities is also subsumed within this. If one can design a clever enough loss function, and indeed it can be done. So although we are looking at relationships of this kind, f less than g, we can easily also find out things such as f equals to g by simply demanding that f is neither less than g nor greater than g. So it's a very simple argument. And with the addition of a clever loss function, one can actually simultaneously look for both equalities and inequalities. Right, I'm sort of almost at the end of my talk, so I'll give a brief outlook on where I see things progressing. So one running theme for this framework seems to be the interplay of theory and experiment. So we are not very clever with our machine learning at the moment, and although we get results, in order to get come up with really powerful conjectures or more meaningful conjectures, we would have to solve higher and higher dimensional problems with loads more data. Mathematical data is cheap, so that's not a problem. But at some point you hit a wall, and the no free lunch theorems in optimization tell you that you might not always get lucky. So we need loads of insights from theory that will drive the algorithm that powers the oracle. So in that spirit, we also sort of try to understand that given the cone structure that is obvious from this space of conjectures and metrics that we can potentially put on this surface to help with geometric gradient descent, is there a relationship between good conjectures and geometric properties of the space? As in, do the good conjectures lie in special places in the conjecture space? And we sort of, without going into too many details, we sort of realized that it's difficult to quantify Robert Dijkgraaf's list of what makes a good conjecture, but there is, and one can make create computational proxies for them. But are they meaningful? But one interesting thing we realized is often, for example, n less than 2 to the n is a legitimate inequality that is true, but it's not tight, it's not sharp. So if we want to come up with only sharp inequalities, Then we suspect that they are related to information about curvature on the space of conjectures. So sort of, very broad strokes, one can say that conjectures have masses that create curvature in your space, and those are the places to look at. So that you get more interesting things like the Collat's conjecture or Ardoustra's conjecture, as opposed to basic things like this. So geometrization is an approach we are taking in this sector. Recently, it was pointed out to me that there are these weird things that I'm only learning about, O minimality, which connect to logic and depend on these constructs called definable sets. So definable sets are effectively sets which can be expressed as solutions of some nice system of equations. And our approach is sort of different. We are fixing the domain, and we are looking at functions that obey inequalities over the whole domain. On the other hand, on definable sets, you're sort of doing the opposite. You're looking at domains which are solutions of interesting systems of equations. So these are some theoretical directions we want to explore. And we're chatting with some folks about this. In terms of representations, we have sort of used a symbolic representation, but people have tried symbolic AI for many decades in the past. But one big advantage that's there now is the natural language representations. So as we have all experienced, ChatGPT is freakishly is freakish. And it's not great at doing mathematics, but it's good at semantic reasoning. And there's lots of work people have done to show that that is indeed the case. So the kind of pipeline I see for this framework is we sort of have a high-level NLP presentation, NLP model guiding us in the search space, and followed by symbolic approaches to really write down a precise representation of a mathematical statement. So this is stuff that we intend to look at. There's also this whole can of worms with proving these conjectures, and all of this is yes.
Yes, just one question about the curvature. So first, what type of curvature you are intrinsic, extrinsic? Can you explain a little bit?
I cannot, because we haven't thought this through. But think of scalar curvatures.
Okay, and so at one point, if the curvature is high, what information you have?
So if the curvature is high, then effectively one can argue that this gives you a sharp inequality as opposed to a trivial inequality.
So does it mean that you land most of the time on that point that has high curvature?
Yes. Yes.
So that's why.
Yes.
Also, infinite curvature might happen in this case?
Infinite, I mean, it depends on your design of your loss. It is possible, but I suspect it might not be smooth enough to work on a regular computer. But what we can say for certain, we have to be more precise when writing our statements about this. But the strictness or the sharpness of the inequality is something that we will desire in whatever conjecture we produce, and this is a good proxy for that is the curvature on the space. Yeah. So right. So different representations are quite interesting. Coupling with proof assistance, we sort of had a lot of conversation here at LIMS with Thomas and Yang about this whole pipeline of mathematical discovery, and the obvious thing to do is would be to couple this this module to a formal proof assistant. But things are in a hope for a proof, but things are pretty hopeless in both the sectors. So we have been chatting with folks working on Isabel at the computer lab in Cambridge. And we sort of realized that the state of the art there is really in completing very short steps in a proof. There are nice functionalities such as with crazy names as well. There's the sledgehammer, which sort of tries to prove a statement that as soon as you encode it in Isabelle. There's also nitpick, which is very good at coming up with counterexamples using clever heuristics. Although in real applications, these things never really work. So in fact, we spent a good half an hour trying to define the prime counting function in Isabelle, and quickly realized that if you ask ChatGPT, it's much faster. And the reason ChatGPT can do this is because Isabelle has a huge repository of proofs and statements in mathematics. Yeah. So nonetheless, coupling with proof assistance is sort of another big aspect, and we hope we can make progress on this. Now, one of my collaborators on this project is an expert in quantum theory. Shubha is just moved from Berkeley to Delft, and he sort of had been bugging us to write everything down as inner products, because down the line, when the quantum computers come, we can take advantage of that. But that's sort of quite interesting, especially in light of the fact that if one emphasizes such representations of computation, then sometimes nice coincidences happen. Looking at the Hadamard matrix, was a bit curious of an observation for us, because it also not only it gives you a nice representation that acts on your functions on your conjecture space, but it also allows you the same structure as you need for if you try to complexify the space. Nonetheless, there's scope for more clever machine architectures in this. As we hit the curse of dimensionality, we've sort of looked at various examples, including some. We're considering some physical examples where one problem that is of interest to physicists or mathematicians is given a physical system, what's the lowest energy level? So we were sort of looking at conjectures about the smallest eigenvalues of certain classes of matrices, and the idea is if we can bound them by more computable quantities, then that's a very cheap computation to do. So we're sort of looking at various kinds of applications, and we've also thought a little bit about what can good conjectures give us. So once we produce these conjectures, can we use them to perturb the conjecture space and guide us towards conjectures of that time? So conjectures beget conjectures, and some of the things that are within the scope of this framework is creating reformulations of different interesting conjectures, for instance. But none of the things we're doing at the moment will lead to automated proofs of these statements. So let's not get too excited. The final point I wanted to mention was about mathematics education, and I'll only talk a couple of lines about this. So one of the perhaps the most ubiquitous way of assessing undergraduate students in mathematics is to give them questions for which answers are already known, and so that's how higher education works, and tried and tested framework. But often one realizes that when it comes to research, then answers are not known. And conjectures can help you think. So one can rethink or reimagine some aspects of assessment in mathematics education by thinking of using this framework or something similar as a tool to generate practice problems for which answers are not known, or exam questions, or pose Olympiad questions, and so on. And it also helps engage the wider community of mathematicians. Terry Tao's polymath project is such a great example of this phenomenon. I should stop soon. So yeah, there are too many limitations to list here, but we've already touched upon various things. So for the moment, we need computable functions. We need to find enough theoretical insights to beat the curse of dimensionality. And when we do work with first order logic or other representations, human readability will be very important. If you cannot make sense of the statement, then that's interesting to accept the veracity of it. I think the ABC conjecture is an example of this. This is the paper that I spoke about, and we'll be doing follow-ups of this. If you have any comments, please reach out to us. So Shubhayan, as I said, he's an expert in quantum theory. He's a friend and a collaborator. Likes ice cream clearly. And Rahul is finishing his PhD in analysis in Stanford, and he's going to move to Berkeley. And they are both incredibly good chess players. So I learned a few lessons. Right. This is a summary of the talk that I will get into, but I'll take some questions. Maybe.